Okay, how's everybody doing this morning? Good. All right, cool. So today we're going to start with a review of advanced DMMs. So we'll talk a little bit about frequency measurements, capacitance measurements, and high current. And then we'll go on to the main topic for today, which is solar panels. So we'll talk about what is solar electricity, why we care about it, and how it works. And then we will discuss solar panels, solar cells, and solar arrays. And we'll also talk about solar array design and some of the math that goes into that. And we'll see that you can put solar panels together in series and in parallel to get the voltage and current that you are looking for. And finally, we'll talk a little bit about efficiency of solar panels and solar arrays. And then we'll do a preview for today's lab after that. So are there any questions before we get going? Okay, cool. So then let's start with a quick review of frequency. So we talked a little bit about advanced features of DMMs last time, and we said that these DMMs could measure several qualities or several things that we hadn't talked about before. The first one was frequency. So we said that if you have a signal that repeats over time, then the frequency of that signal is how often that signal repeats. So for instance, how many times it crosses the horizontal axis going up per second. So if it does that 1,000 times every second, we would say that that is a frequency of 1,000 hertz. Remember, hertz is short for cycles per second. So how often the wave repeats is its frequency. And we found out that we could use the digital multimeter to actually measure that. And we actually did a test. We hooked up the digital multimeter to the function generator, and we wanted to see whether the function generator could create a higher signal than the DMM could measure, or whether the DMM could measure a higher signal than the generator could create. So which one could which one won? Which one was better? Yeah, the multimeter. The multimeter was able to measure a higher frequency than the generator could create. So those multimeters are pretty powerful that we have there. So that was frequency. Any questions about that? All right. Then we also talked briefly about measuring capacitance. So we said that a capacitor is a device that stores energy, and it's pretty simple. It's just two metal plates that are close together but are separated by a thin layer of insulation. And they store energy by having negative charges on one side and positive charges on the other side. And the amount of energy that it can store, this device can store, is called its capacitance. So we'll talk more about capacitors a little bit later in the semester, but this is the basic idea. And we said that we could use the meter to measure the capacitance of one of these little components. So when we used the meter to measure capacitance, did we use these leads and hook up the leads to the capacitor? No. Instead, we plugged the capacitor into these two little holes that are right above the leads. And why did we do that? What was wrong with using the leads or for measuring capacitance? Yeah?
The leads have a slight amount of capacitance.
Exactly. The leads have their own capacitance because they are two pieces of metal separated by a thin layer of insulation. So if you were to hook a capacitor into these leads, then you wouldn't know if you were measuring the capacitance of the component itself or the capacitance of the leads. So because of that, we eliminate the leads and we just plug the capacitors directly into the meter. So any questions about capacitance? All right, cool. So then finally, we talked about measuring high current. So we said that this DMM could measure low current or high current. In the low current, in order to measure low current, you would put the black lead in the common port and then the red lead into this milliamp port here. And then the dial could be in one of two settings. It could go in the 20 milliamp setting or the 200 milliamp setting. So in the low current position, the meter could measure up to 200 milliamps. If you wanted to measure more than 200 milliamps, you need to move this red lead over to the far left-hand port, and then you can measure up to 10 amps. The only trick here is that when the red lead is in the 10 amp port and you're measuring high current, the meter must be in the 10 amp position. That's the only place it can be. It's easy to make a mistake and put it in this other position, and the meter will still show you a number. It won't tell you anything's wrong, but the number will be off by a factor of 10. Okay? So whenever you're measuring high current, the dial needs to be in that 10 amp setting. That's the only place it can be. Okay? So any questions about measuring high current? All right. Cool. So then let's go on and talk about our main topic for today, which is solar electricity. So solar electricity is any electricity that's generated by solar panels. That's really all it is. So why would that be important? Basically, solar panels are everywhere these days. I mean, they're on top of houses, they're on top of commercial buildings. They're just ubiquitous. There was a recent law that was passed that said all new houses that are built in California have to have solar panels on them. So solar electricity is all over the place. It's a renewable source of energy. So it's these solar panels are even used on parking meters and on calculators and things like that. So it's useful to know a little bit about what this is and how it works. So that's why we care about it. So then how does it work? Well, the basic building block for all of these solar, all the solar energy generating facilities is a solar cell. So let me explain a little bit about what that is and how that works. So a solar cell is a little piece of silicon. And it's actually made up of two different types of silicon that are stuck together. One type is called N-type because it has some extra negative charges on it. So that's the N-type. And then the other side has some positive charges on it. What do you think they call that type? P-type. You got it. All right. So we got N-type and P-type silicon here. And what happens is that when you put these two types of silicon together, they create a one-way valve for electricity. This is actually the way that that diodes are made also. And we'll talk about diodes in a later class. But what happens is that when you put these two types of silicon together, they make a one-way valve for electricity so that electrons can flow from this side over to that side, but not the other way around. Okay? So we got these two types of silicon, and what happens is that you got the sun up here, and when sunlight comes down and hits the N-type silicon, it knocks into some of these extra electrons and it knocks them loose. And so they're not in a stable position anymore. They're kind of floating around now in this this silicon that's on the left side here. And so you've got these extra electrons there, and they'd like to get over and combine with these extra positive charges on the other side, but they can't pass through the silicon because it's a one-way valve. But if you take a wire from this side and connect it over to that side, then you give the electrons a path where they can flow. And they flow around this way so that they can join up with the positive charges on the other side. So that's how you create a flow of electricity. And then if you want to do something useful with this, you just put a load in the middle, like your, say, a motor. Yeah, well, yeah, or a battery if you want to charge a battery, exactly, or your cell phone, or a little flashlight, or whatever you want.
So is it,
Yeah.
is it in exchange? Is it due to like anything like heat or anything like that, or is it just
No, it's not heat. It's the
collecting the electrons?
it's the radiation from the sun knocking those electrons loose, and then those loose electrons flowing through the wire to meet up with the positive charges on the other side.
Is this how all solar panels are?
Yeah,
Okay.
yeah. In fact, you asked about heat. Solar panels are actually more efficient when they are in colder temperatures. So, yeah.
Less waste, like less thermal electricity being wasted?
Something. I'm not exactly sure why, but yeah. Yeah, they absorb a very specific wavelength of light. And yeah, and then they do their thing. So this is a solar cell. It's the sandwich of these two different types of silicon. But there's a problem with the solar cell. Problem is that it's not very strong by itself. So it has maybe about a half a volt of potential there, and maybe around 10 to 100 milliamps of current that one cell can generate. So that might be enough to power like a little calculator, say, but it really can't do much beyond that. It's certainly not enough to power a house or a car or anything like that. So if you want to do anything useful, you can't just use one cell. So instead of just using one cell, people combine these cells together. So if you put a bunch of cells together, you can wire them together in different ways to increase their voltage and their current. So if you put several cells together under glass and you kind of wire them together, then that is what we call a solar panel. And you can combine different numbers of cells and put them together in different ways to create different voltages and currents. And one panel might be enough to do a little bit more work. So it might be enough to power a parking meter, say, or one of those little emergency phones that are by the side of the highway. You see those sometimes, or maybe a weather station. So something small like that, but it's still not going to be enough to power a house or an industrial building or something like that. So if you want to power larger things, then what you have to do is you have to put several panels together. So you might end up with, dozens or hundreds of these panels connected together. And we call that a solar array. So that's what you would see on top of a house or an industrial building. So a panel is a group of cells, and an array is a group of panels. And you can make these arrays just about as large as you want. Okay? So,
So
yeah.
this is totally random. This is just for if that's their potential is 0.5 volts, like that's the amount that they can do at best conditions. How much do they usually get, like on average? Because I feel like with atmosphere and everything, that probably has an effect on it. So what's like the normal amount that they actually obtain?
Right. So that's a good question. And we're going to talk more about that in just a second when we talk about efficiency. But yeah, I mean, when you position the cells, you try to position them, or the panels, you try to point them in the right direction and stuff like that. So it might be, yeah, like 0.5 volts when the sun is right overhead and shining right on it. Maybe, 0.3, 0.4 when the sun is off to one side or the other, something like that.
I was reading that United States is contracting with like a lot of other countries to make like a ginormous floating solar farm. That's supposed to be like 2 kilometers, like square kilometers wide in space, and it's supposed to have like 40 or 60% more like potential. So I was wondering if that's because they have just more, they have better solar cells with more, or is it just
Maybe, yeah, or less atmosphere in the way, yeah.
So would it mean that solar cells could have more than 0.5 volt potential?
I mean, so this is kind of like a standard, most common type of solar cell is made with these different types of silicon. But a lot of research is being done these days because the solar panels and solar cells just aren't that efficient. I mean, even the best ones that even the best versions of this kind in ideal conditions are, like maybe 10 or 15% efficient. So that means that they're losing 85% of the energy that hits them. So so people are doing all kinds of stuff to try to improve on that, including different materials, different geometries, and stuff like that. So I don't know about the specific case that you're mentioning. So it's possible that it's a combination. I imagine it's a combination with less atmosphere and maybe different materials and stuff like that. So, yeah. So when we combine these, so in any case, one solar cell that's giving you maybe half a volt and dozens or 100 milliamps is not going to do very much for you. So you want to put it together into a panel. And so the way that this works, the way that this works is that you can combine these cells in different ways in order to increase their voltage, the total voltage or the total current of the panel. So let me talk a little bit about that. That's some of the array design and math. It turns out that this concept works the same whether you're putting cells together to create a panel or whether you're putting panels together to create an array. The concepts are the same. So let me talk about that for a minute. So let's say that I wanted to, say that I have one little cell here, and this cell will produce say 0.5 volts and 10 milliamps of current. This acts almost like a battery. It has a positive side and a negative side, like a battery, and a battery would produce the same sort of thing. A battery would produce a fixed voltage and a fixed amount of current. So this is kind of a bonus lesson, because when we're learning about solar cells, everything we learn today will also be applicable to batteries. So if you learn about this, you'll learn about how you can combine batteries together in order to produce more voltage and more current. Okay? So anyway, we've got this solar cell, and it produces half a volt and 10 milliamps. Say we have a whole box full of these. We can use as many of these cells as we want. We want to wire them together, but we want to make a panel that produces 1.5 volts and 10 milliamps. So we got this whole box full of cells. So the question is, how can we wire them together to create 1.5 volts and 10 milliamps? Yeah.
You could wire 3 of them in series.
That's perfect. Yeah, we can combine 3 of them in series. That's exactly right. The reason that works is because we've got a half a volt difference across each cell, and if we wire them in series like this, then we've got half a volt stacked on top of half a volt, stacked on top of half a volt, which gives us 1.5 volts altogether. So if we were to measure the voltage from the top here to the bottom, we would see that that is 1.5 volts from there to there. So that's how we get the voltage. Now, for the current, we know that each one of these cells produces or allows 10 milliamps to flow. So that means that each cell has 10 milliamps flowing out of it and should have 10 milliamps flowing back in. So that means that right here, there's 10 milliamps flowing out of the bottom cell into the middle cell. And then that middle cell also allows 10 milliamps to flow out of it, and that flows into the top cell. And then finally, that top cell has 10 milliamps flowing out of the top cell. So that means that we would have 10 milliamps flowing through our circuit. If we had a load here in the middle, this would be, the battery that we're charging or the motor that we're turning or whatever. We would have 10 milliamps flowing through that load. Does that make sense? So when we have this series circuit here, the voltage increases but the current stays the same. Okay? So if we want to increase the voltage of our, if we need more voltage than we would get from one single cell, we can wire those cells together in series and get more voltage out. So any questions about that? Okay, so now let's say that we have the same solar cells, but we have a different application. And in this other application, we want to have a panel that produces only half a volt, but it produces, say, 40 milliamps of current. So how could we wire these cells together to make a panel that does that? Yeah. Yeah, that's right. In parallel. Exactly. Exactly. So, so if we put 4 of those cells together, and then we have our load over here, then that should fulfill our needs. So let's see about why this works. So each one of these cells produces 0.5 volts. So there's a 0.5 volt difference from the top of this cell to the bottom. And we have these long wires, and we know that the voltage is constant along any wire. So we could call this point ground, or 0 volts. So then what would be the voltage over there? Right at the bottom of our load. 0 volts, exactly. Because we have 0 volts over here, and we got a wire going all along there. So that's 0 volts all along that wire. And then we've got a 0.5 volt difference across this cell. So what voltage do we have at that point? Half a volt, exactly. Because we start at 0, we go up by a half, so we have 0.5 volts up there. And again, we've got this long wire that runs all the way across the top of the circuit. So, so what's the voltage at the top of our load? Yeah, 0.5, exactly. So 0.5 volts there. All right, cool. So that's the 0.5 volts part of our what we want. So then let's check the current and make sure that we're getting the right amount of current. So each one of these cells produces 100 milliamps. So we have 100 milliamps there. So that means that we have 100 milliamps flowing along that part. But then that meets up with this, the current from this cell, which is also 100 milliamps. So then these two combine, and how much current do we have flowing there?
You mean 10 milliamps?
Oh, I'm sorry. Yes, thank you. Thank you. Yeah. All right. Thank you. So 10 milliamps and 10 milliamps. So what's that? 20, exactly. 20 milliamps. All right, perfect. And then we get another 10 milliamps there. So how much do we have there? 30, perfect. And then we have a final 10 milliamps coming out of this last cell. So that gives us 40 milliamps there. And that's what flows through our load. So that's how we get the 0.5 volts and 40 milliamps. Okay? So we can see that when we wire the panels or the cells in parallel, the voltage stays the same, but current increases. Okay. Like I said, this theory, this strategy applies not only to solar panels, but also to batteries. So just a quick side note. How big do you think one battery would be that goes into a Tesla car? Tesla, you know, Teslas that you see on the street all day. How big do you think one of their batteries is? Yeah.
It goes the hole underneath the car.
Right. There are batteries all over underneath the car, but it turns out that it's not one battery under there. So what's that? Yeah, it's a bunch of different batteries put together. So how big do you think one battery is?
If I remember correctly, the individual cells about yay big.
Right, exactly. The individual batteries are about the size of a AA battery that you would put in a calculator or a flashlight. You know, one of those guys, right? Yeah. Each one of their little batteries is about that big, but they put like something like 2,000 of them together in order to power a whole car.
Only 2,000?
Something like that.
What you're saying is if I had like 1,000 Xbox 360 remotes,
Right.
it'd be quick.
Yeah, you could get somewhere. Yeah, no, yeah, and they do it all using these same principles. They increase the voltage by putting the batteries together in series. They increase the current by putting them together in parallel. And in fact, sometimes you need more voltage and more current. So what do you think you could do if you need more voltage and more current? Series parallel, exactly. So, say you wanted to have a panel that produced 1 volt and 30 milliamps. How could you do that? Yeah, go ahead.
Make 3 arrangements of 2 cells in series and then wire those arrangements in parallel.
Yeah, that's perfect. That's exactly right. So you could have, cells in series like this. And so when you have 2 cells in series like that, each one is 0.5 volts, 0.5 volts. So together, this gives you 1 volt. And then if you put 3 of those in parallel, so this by itself it's 1 volt and 10 milliamps. So if you put 3 of those together in parallel, then you end up with 1 volt and 30 milliamps. And that's the kind of thing that they do with the Tesla cars. They put these batteries together in series and in parallel in order to get the voltage and current that they need. And that's also what goes on inside of solar panels. So you might, I don't know if you've looked closely at a solar panel before, but if you look closely, you can actually see the different cells wired in series and in parallel. So if we were to look at the cells inside of a panel, if we were to look at the panel from the side, like we were to cut a slice right through the side of the panel, we could see these cells. And say this front side was the negative side and the back side is the positive side. Some of these cells are wired together in series. So remember, in order to be in series, the positive side of one cell has to be connected to the negative side of the other cell. So the way that a panel does that is that there are these thin strips of metal, and the metal goes from the positive side of one cell, and it sort of folds around and connects to the negative side of the next cell. So there, you can see that the cells are wired together like this. This is in series. So if you look at a panel, you can see some of the cells are wired in series. Other cells are wired together in parallel. So the way that cells are connected in parallel, remember, in parallel, all the negative sides are connected to each other, and all the positive sides are connected to each other. So if you have cells in a panel and you want to connect them in parallel, you take the same little pieces of metal or foil and you just connect them so that the negative sides are connected to each other and the positive sides are connected to each other. So I'll pass around some of these panels, and you can take a look. You can actually see the way that these connections are made. Okay? So, and on the back of the panel, there's also a rating. So you can see that you can get different voltages and currents depending on how you arrange these cells. Okay? So pass those around. Here you go. And we'll pass this one from the other side.
Do you arrange panels themselves into
Yes.
series and parallel?
Yes, exactly. So this exact same process can be used to arrange panels into solar arrays. Okay, so the only difference is that the panel would start with higher voltage and higher current, but the process is exactly the same. Okay, and in fact, we'll get to do that in our lab today. One other thing I wanted to talk about was the ratings on these panels. So the panels talk about two basic types of ratings. So there is the open circuit voltage and the short circuit current. So these are the ratings on the panels. And let's talk a little bit about what these mean. So the open circuit voltage, well, these are maximum ratings. So the open circuit voltage is the maximum voltage a panel can create. And then the short circuit current is the maximum current that the panel can create. Okay? So let's talk about what those mean and why they're important. So say you've got a panel here, and you wanted this panel to create the maximum voltage that it possibly could. So you've got, a positive terminal here and a negative terminal there. If you put a load here, any kind of load, that's going to it's going to slightly decrease the voltage that's coming from this panel. So the maximum current, or the maximum voltage that this panel could create would be if there is no load here. So when there is no load, that's when you get the maximum voltage. So if you have no load, there's no connection from one side of the panel to the other. And what's another name for a circuit where there's no connection from one side to the other? Yeah, an open circuit, exactly. So that's why we call this the open circuit voltage. That's why the maximum voltage is the open circuit voltage, because you get it when there's no connection, when you have an open circuit from one side to the other. Okay, so that's the maximum voltage. Now imagine that you wanted to have a circuit that is delivering the most current you could possibly have. So if you have a load here, then that load will have some type of resistance to it, and that resistance will make it difficult for the current to flow. So the maximum amount of current that you could get is if you didn't have a load, but you had a straight wire going from one terminal of your solar panel to the other. So this is when you would get the maximum amount of current. And what's another name for a circuit that has a straight wire from positive to ground? A short circuit, exactly. So that's why we call this maximum current the short circuit current, okay? Because it's the amount of current you would get if you had a short circuit from one side to the other. Now, let's talk about how you would measure these, okay? So if you want to measure the maximum current, well, you're going to make a current measurement. So you're going to have your meter over here. And remember, a current measurement is a destructive measurement. So you have to partially deconstruct the circuit to make it. So you would break the circuit apart right there, and then you would attach your meter from one side to the other, and then you would put your meter in current measuring mode, and so that's how you would measure the short circuit current.
Why would you want to put it in short?
Why would you want to put?
Like make it short circuit.
If you're trying to measure the maximum amount of current that the panel can create, this would be the maximum that it could do.
Is it only okay to do that because there's some sort of resistance in the multimeter?
There's actually a resistance in the panel itself.
Okay.
Yeah. So this panel behaves kind of like a perfect battery and a small resistor combined together. And so because of that, we can measure the short circuit current this way.
When you're saying small resistor, like what equivalent of resistance would you think? Like range?
Well, so it depends on the cell. So, but you can make that calculation. So, for instance, if we had a cell that was producing 0.5 volts and 100 or say 10 milliamps, what that really is you're saying that you've got like a battery here that's 0.5 volts and a resistor, and this whole thing is producing 10 milliamps. So we can use Ohm's law to calculate the resistance. So we would say R equals V over I. So that would be 0.5 volts over 10 milliamps, or 0.01 amps. So that would be 50 ohms. So that's how you would figure it out. So we're actually going to make open circuit voltage measurements and short circuit current measurements for these panels. So you could actually calculate this theoretical resistance for the little panels if you wanted. So anyway, that was a little bit of a diversion, but the point is that this is the way that we measure short circuit current. You connect the two leads of the panel to the two leads of the meter and put it in current measuring mode. Now, the way that we measure open circuit voltage the open circuit voltage would be when the panel was like that. And remember, the way that we measure voltage with the meter is we just connect the two leads of the meter to the 2 points that we care about. So in this case, we'd connect the meter to the two ends of the panel. Does that look familiar? Same connections that we had in the last one, right? The only difference is that in this case, the meter is in voltage measuring mode, and before it was in current measuring mode. So this is the open circuit voltage measurement. Okay? So those are how we make those measurements. So any questions about that? All right, cool. So we've talked a little bit about solar array design math, and we talked about putting panels or cells in series and in parallel. So now I want to talk briefly about efficiency. So efficiency is how much energy a cell is producing, or a panel is producing, relative to the amount of energy that hits it. So there are a number of things that affect how much energy a cell or a panel or an array can produce. Kind of the first and most important is how much sun is actually hitting it, and at what angle. So if you have your array out in a big open field and there's lots of sun, that's probably a good thing. If you got it up on a roof that's underneath a tree and it's in the shade, it's probably not going to get very much energy. And there are meters that exist that can measure how much energy is hitting at a particular spot. So this is one of those meters. This is called a day star meter. Anybody know what the day star would be in this case?
The sun.
That's right, the sun. It's the star that you see in the daytime. So anyway, they call themselves day star meters here. So this will tell you how many watts of energy you're getting per square meter. So right here, we're getting about 0. I mean, the light is so low that this meter isn't registering anything. If we come over here and we put it up close to the fluorescent lights, now we're getting 12 or 13, something like that. How much do you think we could get if we went outside on a clear day? Any guesses?
50.
Yeah, maybe 50?
100.
Yeah, 100? Huh?
At least 2.
100, 100. We got 200 over here, 200 over here. Do I hear 300? Anybody got 300? 300. I was in the back. Anyway, yeah. 301. We got, yeah. No. Yeah, if you're lucky, on a good day, you can get up to 1,000 watts per square meter. So yeah, on a clear sunny day, it's just, yeah, you can get a whole bunch. Okay. So
Highest the machine detects, or is that just the highest that it'll get to?
that's about the highest it'll get. Yeah. So so that's the amount of energy that's coming down from the sun and actually hitting your panels. But not all of that is actually turned into electricity. So the amount of that energy that actually gets turned into electricity is determined by the efficiency of your panels. So if you're getting 1,000 watts per square meter and you have 1 square meter of panels, and that panel was producing 500 watts of electricity, that would be 50% efficient, because you're getting 1,000 watts coming in and you're only getting 500 watts going out. Like I said, in real life, solar panels are pretty inefficient. You get maybe 10 or 15%. So if you were getting 1,000 watts of electricity, of sunlight hitting that square meter, you might get 10 or 15 watts out. And there are a number of factors that affect that efficiency. One of the most important is the angle. So if I have this meter and it's up here and it's pointed straight at the light, I'm getting about 13 watts, 14, something like that. If I start to turn it, if I'm at a 45 degree, now I'm at 7 watts. Just that much angle gives me 7 watts. Over here, I'm down to 4 watts. And then pointing sideways, I'm at 1 watt. So the angle makes a big difference. Also, dirt and debris that cover the surface of your panel can really get in the way. And like I mentioned earlier, there are different chemistries and different materials that are being used now to try to increase that efficiency as well. So all those things make a difference. Yeah.
Is there a thing for like solar panels to be only for nighttime, so when it's dark it would be energized?
To
Like little garden lights you would have in your front porch or something?
Oh, yeah. So what happens with those is that they have a solar panel on top that receives energy from the sun, and they have little batteries inside, and they also have like a light detector. So during the daytime, the solar panel receives the energy from the sun and it charges up the batteries. And then at night, when it detects that it's dark out, it stops charging the batteries, and it has a little electronic switch in there, and it turns on the lights, and it uses the electricity from the battery that it charged up during the day to power those lights. Yeah. And actually, there are similar strategies for houses. You can buy Tesla battery walls now, or power walls that are essentially large battery packs for your house. And it's exactly the same idea. During the daytime, the solar panels charge up that battery, and then you can use energy from that battery at night when the sun is no longer out. Yeah. So efficiency can be affected by a lot of different things, but really efficiency is just the amount of energy that you get out compared to the amount of energy that is hitting your system. Okay. So any questions about that? All right, so then let's go on and do a preview of today's lab. Okay, so the first part of the lab is to use this Daystar watt meter to check the amount of light energy that we're getting inside the classroom. So you're going to measure that. And then the next thing is that you're going to hook up the meter to one of your solar panels. So each group will get a pack of 4 solar panels. They look kind of like this. And we'll be using these solar panels for this lab. So you'll hook up the DMM to one of your panels like this, and then you'll measure the open circuit voltage of this panel, and then you'll measure the short circuit current for the panel as well. And so we're going to do that for all 4 of the panels, actually. And it would be good to do these outside in the sun, okay? So we're going to hook up each panel and measure the voltage and the current in the sun. And actually down here, instead of doing this one in direct sun, we'll just do one inside, okay? So this bottom one will be inside the classroom. All the other ones will be out in direct sun, because we're going to be using, we're going to be hooking these up in some other circuits outside, and it'd be nice to know the individual values for these panels before we hook them up in circuits, okay? So that's the second part of the lab. So you're going to measure the voltage and current for each of the panels outside in the sun. So questions about that? Okay. So then, right. So then, yeah, so these, where this says in direct sun, just that'll be inside, okay? These will both be inside. And then how do you account for the difference? And then after that, we're going to start measuring the voltages and currents in series and in parallel. So we're going to be outside for this. It's a beautiful day. We're going to get to go outside and enjoy some of the sunlight when we're doing our solar panel experiments, okay? So here you'll already know the voltage and current for one of your panels, and then you're going to connect that panel to another panel in parallel, okay? So let me show you how we're going to connect these panels in parallel. Remember, parallel means that the positive terminals are connected to all other positive terminals, and negative terminals are connected to all other negative terminals, okay? So if we want to connect 2 panels in parallel, we're going to take their positive wires and just twist those wires together. So I'm going to take the red wires from both panels and twist them together. I'm going to take the black wires from both panels and twist them together. And now these 2 panels are connected in parallel, okay? So that's all you do to connect the panels in parallel. If you wanted to connect 3 panels in parallel, you would do the same thing, but now you would take all 3 red wires and twist them together, and all 3 black wires and twist them together, okay? And then that's how you would connect these 3 panels in parallel. So any questions about that? Okay. All right. So that's how you connect panels together in parallel. So you would do this for 2 panels and then measure the current and voltage for these 2 panels. And then you would do it for 4 panels. And you would measure the current and voltage for 4 panels in parallel. So when you're hooking up your meter to make these measurements, for parallel, you would just hook the positive lead of the meter to this bundle of red wires, and you would hook the negative lead of the meter to the bundle of black wires. Okay? That's how you make the measurements. So it's very beneficial for this lab especially to work in groups, because you can imagine that it's really hard to try and hold these panels and connect to the meter and record your data all at the same time. All right? So it's much better if one person kind of holds the panels and gets them lined up with the sun, and then another person, you know, hooks up the meter and makes sure that that's working right, and then maybe a third person can take data. Okay? So I highly recommend that you work together in groups when you're doing this lab. So that's how that works. So any questions about hooking panels together in parallel? All right. Then the next part of the lab is to hook panels together in series. So remember, series means that the positive terminal of one panel is connected to the negative terminal of the second, and then the positive terminal of the second panel is connected to the negative panel of the third, and so on. So if you want to connect these panels together in series, what you do is you take one panel and you take the red lead from one panel and wire it to the black lead of the second panel. So you just twist those 2 wires together. And then you would take the red lead from the second panel and connect it to the black lead from the third panel, and just twist those together. So that's how you make the series connection. You connect red to black and then red to black. And then when you're going to make measurements, you would connect the meter to the black lead on one side of this whole circuit, and then the red lead that's sticking out on the other side of the circuit. Okay? That's how you make those measurements. Also, when you are holding these panels, it's important not to cover up any of the cells in the panel, because the electricity is flowing through each of these cells, and if you cover up one of them, you're blocking that cell, and so you're essentially blocking the electricity for the entire circuit. So, you know, it's tempting to hold these cells kind of like this, but when you do that, you're putting your thumb over some of the cells in your panel, and that can be blocking the electricity. So if you are getting weird readings and you're not seeing any electricity, check your hand position. Make sure that you're not blocking any of the cells, okay? And like I said, try to point these towards the sun, because the angle of the panel makes a big difference to the efficiency as well, okay? All right, so you're going to measure the current and voltage for one cell, and then 2 in series, and then all 4 in series, okay? So any questions about that? All right. And then after that, you're going to design a couple of solar panel arrays.
I did it earlier.
Yeah. So exactly. So you're going to look at what is required. So in this case, it would be 20 volts and 200 milliamps. And you're going to come up with designs for how you would put solar panels together in order to achieve these results. when you do this, you should assume that each solar panel produces 5 volts and 100 milliamps. So let me write that down. So, yeah. So each panel produces 5 volts and 100 milliamps. Okay? So assume that when you are making these designs. And then I'd like you to draw the way that these designs would go, kind of the way that I drew the designs up on the board. So you can draw simplified panels that just have, each one has a positive and a negative terminal on it, and then show how you would connect these panels together and how many you would use to produce these different outputs. So the first one would be 20 volts and 200 milliamps. The next one is 10 volts and 800 milliamps, and so on. Now, for the bottom one, this says build it. We don't have to build it, okay? So you can cross that out. So just show the design again, but you don't have to build it, okay?
You don't have to test the voltage and current of it?
No, no. And then there's one more here, 15 volts and 400 milliamps. And then 3 things you learned in this lab. And and then the last thing is, why is it so important to correctly connect the solar panels for voltage and current when setting up a system? Well, if you didn't hook them up correctly, then you wouldn't get the voltage and current that you need. So you might have less voltage or less current than you were looking for, right? So that's the lab for today. Any questions about that? All right, then I'll take attendance and I'll let you go.